Hello, I'm Paul Beckwith. Now, in this video, I'm going to talk all about the Antarctic Circumpolar Currents. So it's basically an enormous ocean current, enormous in scope and size and influence on the planet's climate. And previously I've talked about the Antarctica bottom water formation, how that is actually decreasing over the decades, and this is a concern for slowing down the overall thermohaline circulation system of the ocean. We've also seen a decrease in the AMOC, the Atlantic Meridional Overturning Circulation. And this is very concerning because if it passes the threshold and shuts off, it basically, all bets are off on what will happen with the climate. We get a massive cooling in the Arctic. But what I'm talking about this time is mostly the surface currents extend, but they do extend down and they cause a lot of mixing of the water. So it's another key part of the ocean current puzzle, building on my previous videos on the AMOC, on the thermohaline circulation, and also on the currents in the oceans in the southern hemisphere. So let's get right into this paper. A new peer-reviewed paper came out. An extensive study looked at the Antarctic Circumpolar Currents. But before I go there, well, let's go there now. Let's have a look. Okay, so this is the article that came out from the Columbia Climate School, Climate, Earth, and Society, State of the Planet. Basically, key ocean current contains a warning on climate from March 27th. This is what I was going to talk about until I saw, at Columbia, James Hansen had put out a new letter, so I went and did that video instead. So this time I'm talking about this key ocean current known as the Antarctic Circumpolar Current. It carries more than 100 times as much water as all the world's rivers combined. All the world's rivers combined is about, 1 to 2 million cubic meters per second flow rates. So this ACC, Antarctic Circumpolar Current, carries between about 164 and 180 odd Sverdrups, where Sverdrup is 1 million cubic meters per second flow rate. So this is a huge water flow we're talking about, circumventing Antarctica. It reaches from the ocean surface to the bottom. It measures as much as 2,000 kilometers across, connects the Indian, Atlantic, and Pacific Oceans. So it plays a huge role in regulating global climate. So it continuously swirls around the southernmost continent of Antarctica. It's by far the world's most powerful and consequential mover of water. In recent decades, it's been speeding up. Okay, so as we get global warming accelerating, the ACC current is speeding up. But scientists are really unsure whether that's connected to human-induced global warming. I'm sure it is. And whether the current might offset or amplify some of the warming's effects. Okay, so that remains to be seen. So a new study came out that was just published, peer-reviewed study, international research team. They did a very interesting measurements of indirect measurements of this current over the last 5.3 million years. Okay, so what they did is they used sediment cores from the planet's seafloor in the roughest and most remote waters to chart the ACC's relationship to climate over the last 5.3 million years. So what they find is a key result, the elevator pitch, if you like. During past natural climate swings, from glacial periods to interglacial periods, etc., the ACC, the Antarctic Circumpolar Current, it's moved in tandem with Earth's temperature. So it slows down. It's been slowing down during cold times, during glacials, and it gains speed in warm ones. Speed ups that were associated with major losses of Antarctic's ice. So today's speed up that we've seen occurring over the last number of decades, that will continue as human-induced warming proceeds, and that could hasten the wasting and loss of Antarctica's ice. It can increase sea levels more rapidly, and it can affect the ocean's ability to absorb carbon from the atmosphere. There's huge amounts of carbon. In fact, 40% of the carbon that goes into the atmosphere is absorbed in the southern hemisphere by the downwelling processes by the ocean, the biological pump, if you like. Okay, so the findings are published in the journal Nature. So this is from the bow, the front of the drill ship, called the Joides Resolution, which was doing its drilling in the far southeast Pacific Ocean to get this 5.3 million year record from the ocean sediments. So this current, the ACC, the Antarctic Circumpolar Current, is the mightiest and fastest current on the planet. It's arguably the most important current of the entire Earth climate system. Okay, so this study implies that the retreat or collapse of Antarctic ice is linked mechanically to increased flow of the Antarctic Circumpolar Current, and we're seeing this happening. The current is increasing as global warming proceeds and accelerates. The conditions for the ACC were set about 34 million years ago because continental drift, tectonic forces, separated Antarctica from other continental masses further north. Okay, so Antarctica was connected to, we can look at the map and see where it was connected. Okay, obviously it was connected here. South America here, there was no ocean. These pieces of land were connected. Continental drift moved Antarctica away, opened up this passage, and then of course the currents could start to flow. So this key change happened about 34 million years ago. So the ice sheets, the current started around Antarctica. It isolated the continent. The ice sheets began building up. The current sought to have started flowing in its modern form 12 million to 14 million years ago, after the continental drift sufficiently carried Antarctica far enough away. Driven by the continuous westerly winds. Westerly winds are from the west, flowing west to east, circumventing the continent. So if you're looking down on Antarctica from above, it's clockwise. You see a clockwise current from west to east. There's no land in the way, so this current, there's nothing to really slow it down and stop it apart from topography. So the current, the ACC, it circles Antarctica clockwise as seen from the bottom of the Earth at about 4 kilometers per hour. That's 2.5 miles per hour. And it carries 165 million to 182 million cubic meters of water each second. 1 million cubic meters of water a second is a Sverdrup, so it carries 165 to 182 Sverdrup. If you divide that by 100, you get 1.65 to 1.82 Sverdrups. That's about the current flow of all of the rivers on the planet combined. Now, scientists have observed that the winds over the Southern Ocean have increased in strength about 40% in the past 4 decades. So this has speeded the ACC, and it's also energized these large-scale eddies or swirls in the current. And those eddies move relatively warm waters from higher latitudes closer to Antarctica, thus closer to the floating ice shelves, which of course the ice shelves are what holds back the vast interior glaciers. So in parts of Antarctica, especially in the west, these warm waters are eating the undersides of the ice shelves, which is the main reason they're eroding away. They're melting out. It's not warming air temperatures, right? The air temperature over the ice is still much below zero. It's the warming water underneath that's melting and undercutting the ice from below. There's an analogy. If you leave an ice cube out in the air, it takes quite a while to melt. If you put it in contact with warm water, it goes rapidly. I'd carry that forward and say if you put the ice cube in the air and the air is well below zero, it doesn't melt at the top. But if it's in warm water, it melts from below. This loss of ice can be attributed to more heat transport to the south. A stronger Antarctic Circumpolar Current means more warm, deep water reaches the ice shelf edge of Antarctica and undercuts the ice from below. Through a complex set of processes, the ocean waters ringing Antarctica also currently absorb about 40% of the carbon that humans introduce into the atmosphere. Okay, 40%. It's a huge biological pump or a huge sink for carbon in the southern hemisphere, you know, for the whole planet. It's vital for the whole planet. You know, trees take out about half, right? And the rest stays up in the atmosphere ocean system. Some of it, you know, if it's in the atmosphere, higher concentrations of CO2, it also means that more is in the ocean, increasing the acidification. Now it says here, it's unclear whether the speed up of the ACC will compromise this 40% of the carbon, but some scientists fear it will. It probably will, right? Everything's connected. Now this shows some of the ice cores that are cut in half. These are fresh, they're not ice cores actually. Sorry. These are the sediment cores from the seafloor. Just the way the light was on them, some of them look like ice, but you can see the grayness. These are the sediment cores, different colors with different depths. They go down 150, 200 meters. So these are the sediment cores from the seafloor that are aboard the drill ship, the Joydes Resolution. So how do they reveal vigorous currents during warm times and slower ones during cold? Well, when the currents are stronger, then there's fewer small particles in the that settle onto the seafloor, right? They're carried by the stronger waters. So you can look at the particle size distribution in the sediment cores, and if you get very, very fine sediment particles, small particles, you know that the ocean currents were slow at that time, so those small particles could settle. And in areas where there's no small particles, just the larger ones, the ocean currents were stronger. Okay, so this is how you can determine from the particle size you can get a proxy for the speed of the Antarctic Circumpolar Current. So this is a huge study, you know, on these big drill ships, 40 scientists from a dozen countries, all with different expertise. On the drill ship, the Joydes Resolution, they gathered ocean floor sediments underlying the ACC near Point Nemo. Now, Point Nemo is an interesting place. It's a spot in the far southwestern Pacific. It's the furthest spot from land anywhere on the planet. The closest land is 2,600 kilometers away, and it's the Pitcairn Islands, a very small islands. Remember Mutiny on the Bounty, Pitcairn Islands. Okay, so the 2-month cruise actually took place in May to July 2019 during the Australian Southern Hemisphere winter, while there was little daylight and waves as high as 20 meters hitting the ship. Okay, so the data was taken, this is about almost, 4 years plus away, almost 5 years away, and the data is coming out now. So these studies are pretty intense, and, the data is actually, it takes years to analyze the data. So the drilling ship's crew, they dropped a drill string 3,600 meters from the ocean surface, so the water was 3.6 kilometers deep, went to the ocean floor, drilled, penetrated the floor, drilled down, removed sediment cores measuring about 150 to 200 meters long each. Then they used advanced X-ray techniques to analyze the layers built up over millions of years, going back about 5.3 million years. Smaller particles tend to settle during times when the current is slower, sluggish, larger ones when it is fast. So they can chart scores of changes in the Antarctic Circumpolar Current speed over time. They can see it going up and down. Compared to the mean flow over the past 12,000 years, it's been pretty steady. This is a period since the last ice age encompassing the development of human civilization, right? The last 12,000 years, the Holocene. Flows dropped by as much as 1/2 during cold times, and at times they nearly doubled during warm periods, actually 1.8 times. Okay, so this shows you the, this is showing you the Antarctica from above. You've got these currents flowing west to east. These are the drill sites here. This is where Point Nemo is, the furthest from land. You can see Antarctica and the ice shelves across here, and you can see fluctuations in the current and the velocity. Here's the velocity, 1993 to 2015 average. You've got some areas that are streaked hot fast, but the general flow is somewhere, you know, in this range. I mean, there's lots of, you know, if you average it out, you know, you're somewhere down in this range here typically. But again, there's been fluctuation, either half that or double that, going back in time. So they used some previous studies done on the West Antarctic ice sheet, you know, the growth and decline of it during glacials and interglacials, and they correlate fast flow periods of the ACC with ice retreat. Colder times, when the glaciers advanced, the ACC was lower. The warmest extended period in the 5.3 million year record was during the Pliocene, about 2.4 million years ago. After that, there was the Pleistocene, where dozens of chilly glacial periods alternated with so-called interglacials. Temperatures rose, the current speeded up, and the ice pulled back. Of course, much of the West Antarctic ice sheet is frozen to land that's below sea level, so it's highly susceptible to invasion and melting by warm ocean waters penetrating underneath. It says, were it to melt entirely, it would raise global sea levels by 190 feet. This is if both West Antarctic and East Antarctic ice sheets melted. There's about 5 meters of ice embedded in the West Antarctic ice sheet, about 7 meters in Greenland. And if you add it all up, including East Antarctica and mountain glaciers, you know, you're talking about 70 to 80 meters of sea level rise. Okay, so we can expect that with further increases in global warming, we'll get further increases in the ACC flow. And if that actually happens, then there's likely to be much faster ice melt in Antarctica. Okay, so that's the key points of this new paper. Now I'll look at the peer-reviewed paper in a minute, but first I'll show you a couple things. So just playing around on Google Earth, right? So you can see Antarctica here, and I measured some distances here with the ruler function. So let's have a look. So this is the Antarctica Peninsula connecting with South America here. And you can see if I click on this line here, you know, you can, okay, how come, let's see. How come I'm not seeing it here? Untitled measurement. There we go. 853 kilometers. Okay, so the distance here is about 853 kilometers, just to give you an idea. This is the Drake Passage, the narrowest part, the narrowest channel, basically, for current flowing around Antarctica. You know, we can go and look at the distance to New Zealand here, about the same distance to Australia. And if we go here, and this is 2,558 kilometers, 2,500 kilometers. And if we go over to here, to South Africa, it's, yeah. How come it's not? fly to. How come it's not changing my measurement? Well, let's do this instead. Let's go over here. Let's do a new measurement. Let's get rid of this. Let's do a new measurement. Let's go over here. Click on this. Click over here. And over here. Almost 4,000 kilometers, okay? 3,929 kilometers. Okay, so you can see the distance, the vast distances involved here. Playing around with Google Earth and the measurement tool. Earth Nullschool is what I showed you at the beginning of the video, and I've set it to look at the oceans. I'm looking at the wind and the currents, and I've got these two numbers here. So at this location here, the wind speed is 67 kilometers an hour, and the ocean currents are 0.78 meters per second. So let's zoom in on some specific regions. Okay, you can see that's meters a second. We could go to kilometers an hour, okay, to make more sense. And you can see 2.8 kilometers an hour. You can see the whirls, and the reds are, you know, faster here. So let's see here, 4.9 kilometers an hour. Okay, but the bottom line is you can see the ocean, you can see the airflow, okay, circumventing the planet, right? This is the wind, basically. And the wind is driving, you know, it's the main mechanism driving the circumpolar ocean currents. And you can see, you know, you can see the variation, you can see the loops and whirls and things spinning off, etc. But the general average flow is around this way at about, say, 4 kilometers an hour. Okay, so this is a vast ocean current called the Antarctic Circumpolar Current. When I talked about the Antarctica bottom water formation, that was from the thermohaline circulation. And you have these chimneys descending around Antarctica, feeding the water, the abyssal water, the water at the very bottom of the ocean. And that's been slowing down over time, right? And that drives the thermohaline circulation of the ocean. This is something different. These are mostly surface currents, but they do extend deep down to the abyss. They cause a lot of mixing, okay? And these currents are actually speeding up as we get more and more warming. So it really complicates the picture. Now, I talked about Point Nemo. So Point Nemo is a location in the ocean that is furthest from land, named after Captain Nemo of 20,000 Leagues Under the Sea by Jules Verne, an awesome book. There's a location in Lat Long. So it's about 2,688 kilometers, which is 1,450 nautical miles from the nearest land. Ducie Island, which is part of the Pitcairn Islands to the north. Moto Noi, one of the Easter Islands to the northeast. And Maher Island, part of Antarctica to the south. You can't get further away from land than Point Nemo. So this is a good trivia fact. The International Ocean Discovery Program, it used to be IODP, being International Ocean Drilling Program. They changed it to Discovery, I guess. The Geordes Resolution, and this was the expedition, May 20th to July 20th, 2019, and all kinds of information on the scientists on board, photo galleries, what they did, what they hoped to accomplish from the proposals and what they actually did, ship reports, daily, weekly, right? There's all kinds of data if you're curious about that scientific expedition. The West Antarctic ice sheet, a lot of that information is from the ANDRIL, the Antarctic Drilling Project, a scientific drilling project in Antarctica, finding information about cooling and warming periods by doing ice cores through the ice, and also going through the sediment and rocks at the very bottom getting a virtually continuous ice core record from the present to nearly 20 million years ago by going through the rocks and so on. I thought it only went back about 1 million years, but anyway, they talk about the Joides resolution work, and you know, lots of details about that. Okay, but that's to get more information on the ice sheet. And then this is an article that's very interesting, and it talks all about the Southern Ocean. It's actually the chapter of a book. It's 41 pages long. I'm not going to go into detail on this, but it's got all kinds of information on the different currents and so on, ocean currents, and data on Antarctica, Southern Ocean, as far as a carbon sink goes. I may do a separate video on this. I think I probably will. But just keep telling you, there's lots, you know, it's chock full of information on the Southern Oceans. This article from a few years ago talks about how the Antarctic Circumpolar Current helps keep Antarctica frozen. It kind of isolates Antarctica. So the ACC, the Antarctic Circumpolar Current, it's the strongest ocean current on our planet. It extends from the sea surface to the bottom of the ocean. It encircles Antarctica. It's vital for Earth's health because it keeps Antarctica cool and frozen. It's also changing as the world's climate warms. So how it affects the future of Antarctic's ice and the world's sea levels, that's the big question. It carries 165 million to 182 million cubic meters of water every second, which is a unit of called the Sverdrup. Carries it from west to east, more than 100 times the flow of all rivers on the Earth. It's the main connection between the Indian, Pacific, and Atlantic Oceans. The tightest geographical constriction through its current flows is the Drake Passage, which I showed you on Google Earth. Only 800 kilometers separates South America from Antarctica, and that's where, you know, that land was actually joined 34 million years ago when it split apart from continental drift. So that completely changed the climate on Antarctica, that break. It was vital to open up the ocean passage to get the current starting to form, although the present form of the ACC has only been around for 12 to 14 million years, but it started flowing, it would have started flowing shortly after the continental drift, although that's a slow process that takes a long time, right? It's not an instant thing. So a satellite view over Antarctica reveals a frozen continent surrounded by icy waters. When you move northward away from Antarctica, the water temperature rises slowly at first and then rapidly across a sharp gradient. It's the ACC that maintains this boundary. So you can see the water temperature, ocean surface temperature in degrees Celsius, right? You know, very, very cold is the blue, and then the lighter blue, it's warming up, and then boom, it shifts, you know, very, very sharp boundary change. Okay, so you can see that's the situation. The ACC and the Antarctic Circumpolar Currents created by the combined effects of a strong westerly winds across the Southern Ocean and a big change in surface temperature between the equator and the poles, right? That temperature gradient is key. Ocean density increases as the water gets colder and it gets saltier. The warm, salty surface waters of the subtropics are much lighter than the cold, fresh waters close to Antarctica. So you get these density gradients, right? There's sharp changes in water density known as fronts. The subantarctic front to the north, the polar front further south, are the two main fronts of the ACC, the black lines in the images. So we've got the subantarctic front and the polar front. And you can see how basically the polar front, the water gets much, much colder quickly as you cross the polar front, and subantarctic front being up there, or subantarctic front, yeah, to the north. And these fronts split into 2 or 3 branches in some parts of the ocean, merge together in other parts. Okay, so we can figure out the density and speed of the current by measuring the ocean's height using altimeters. denser waters sit lower, right? They're heavier, they're closer to the center of the Earth. Lighter waters stand taller. The differences between the height of sea surface give the speed of the current, right? Because there's a gradient there. So this is the current flowing from west to east in centimeters per second, the mean from 1993 to 2015. And you can see the different colors and the streaks, and as I was showing you Earth Nullschool, you could see that sort of thing. Although in Earth Nullschool, it's showing real-time stuff, and you see a lot more of these tight gyrations, if you like. You know, these tight whirls and things going on. This is an average view, of course, so you don't see all of the details there. Okay, the path is a meandering one because of the steering effect of the seafloor, instabilities in the current. The ACC also plays a part in the meridional overturning circulation, which brings deep waters formed in the North Atlantic southward into the Southern Ocean. Circumpolar deep water carried around Antarctic rises to the surface south of the polar front. And, you know, the current is changing. The ACC is not immune to climate change. The Southern Ocean has warmed and freshened in the upper 2,000 meters. Rapid warming and freshening has also been found in the Antarctic bottom water. That's AABW, the deepest layer of the ocean. Waters south of the polar front are becoming fresher due to more rainfall, and waters to the north are becoming saltier from increased evaporation as the planet warms. These are anthropogenic effects. Okay, the ozone hole plays a role, right, in the amount of sunlight that gets through. The winds have strengthened by about 40% of the Southern Ocean over the past 40 years, but they say this is not translated into a 40% increase in the strength of the ACC. There's an increase in eddies that move heat towards the pole in hotspots like the Drake Passage and some other places, the Kerguelen Plateau between Tasmania and New Zealand. Okay, so the question is how much and at what rate will it continue to change? Okay, so that's interesting. So this is the paper now. So let's look at some of the details of this paper. So this is just came out 27th of March 2004. So that's like almost 5 years since the sediment cores were taken by the Geordie Resolution drilling ship on that 2-month expedition. And so let's have a look at, so lots of authors. The Antarctic Circumpolar Current is the world's largest ocean current system. It, of course, affects global ocean circulation, climate, and Antarctic ice sheet stability and instability. The dynamics are controlled by atmospheric forcing, right? The winds, the ocean density gradients, and the eddies. So palaeoceanographic reconstructions, that's of the seafloor sediment, show regional heterogeneity in the ACC position and strength over these Pleistocene, glacial, interglacial cycles. So the currents change, it's strengthened, it's weakened, its position has changed, but the long-term evolution is not that well known. So this is a very sort of important study to try to tease out get more information on how its evolution, how it's changed over time. We know that it didn't exist 34 million years ago because the Antarctica was connected to South America. So they look at the strength in the ACC from sediment cores that they take. They find there's no linear long-term trend in the flow since 5.3 million years ago. Okay, but there was a reversal on a million-year time scale from increasing strength of the ACC during Pliocene global cooling to decrease during early Pleistocene cooling. So this shift, there was basically a Southern Ocean reconfiguration that altered the sensitivity of the ACC to atmospheric and oceanic forcing. It turns out that's probably tied to the increased northern hemisphere growth of ice. The changes are closely linked to 400,000-year eccentricity cycles from the Earth's orbit. And that probably originates from modulation of the precession of the Earth changes in the South Pacific jet stream, linked to Pacific temperature variability. Okay, they saw these huge changes in the mid-Pleistocene transition called the MPT. Yeah, so let's have a look at the results from the graphs and so on. Okay, so I mean, I'm not going to go through, there's lots of details of what they've done. Some of the definitions are the SWW is the southern westerly winds. Talk about the Ekman flow, right? You can use the right-hand rule as things are moving, wind blows, water moves, rotates to the left in the southern hemisphere, generates this Ekman flow, which can change the sea surface heights, etc. Yeah, so anyway, let's have a look at this. So this is some definitions of the modern Antarctic Circumpolar Current. So this is a simulated ocean velocity, 100-meter water depths, right? These swirls here going around in a clockwise direction. The winds are blowing this way. The ocean currents are blowing this way. I showed you on Earth Nullschool. There's a couple locations here where temperature changes significantly. I showed you the temperature decreasing as you go towards Antarctica. This is the northern boundary. This line here, this is the sub-Antarctic front, SAF. Then we have the polar front. Then we have the southern ACC front here. And then we have the southern boundary of the ACC. Okay, and then, you know, during winters, the ice shelves can extend quite far out, as we know from Antarctica. So those are some definitions. Okay, and so they look at the grain sizes in the sediment cores to as a proxy for the reconstructing the Antarctic Circumpolar Current strength. Okay, so here's some of the results. This is the age 0 to 350,000 years ago. And you can see this is the temperature, so it's showing 3 cycles where, you know, it's cooler periods. These are the glacials here, 3 glacials, the interglacial periods here. Okay, so this would be the, you know, the Eemian here and the previous interglacial. So this is temperature. And this is the CO2 level on this curve. So where it's cold, the CO2 level is colder, but close to 180 to 200 ppm. Where it's warmer, it's 280, right? Never goes outside of that 280 zone. Of course, we're much higher now. And this is the Antarctic Circumpolar Current, the strength in centimeters per second. So you can see how it varies from a low of about 4 centimeters a second to a high of about, you know, 9 centimeters per second or so during the interglacial period. So as it gets warmer, the current increases in strength. As it gets colder, the current decreases in strength. Okay, so there's that. This goes back and shows you, going back 1.5 million years ago, 1,500 kiloyears, or 1,000 years. So that's 1.5 million years ago. And you can see the variations in the strength of the Antarctic Circumpolar Current, variations. Okay, so there's lots of, you know, lots of fluctuation, and we can see how that changes over time. This is going back 5 million years ago, the full data set here. So we've got a couple things happening here. This is the initiation of the northern hemisphere glaciers. This is the mid-Pleistocene transition where the things seem to change rapidly there. Another big change seems to occur here. You can look at the ice volume fluctuation, right? It's higher frequency, lower frequency. So the northern hemisphere definitely has a large effect, the northern hemisphere glaciation. And these diagrams are good explaining what kind of happens. So this is the early Pliocene when it's a bit warmer. Okay, so you can see the Hadley cell extending here. basically from the equator down to about close to 40 degrees south, also 40 degrees north. And you can see the wind current, you can see the polar front, the northern boundary, and the currents here, the Antarctic Circumpolar Currents. These are the drill sites right here, a couple of the drill sites, and you can see the Antarctic ice sheet and the sea ice here. Now, as we go to the late Pliocene, it gets colder. So the ice sheet is growing. The Hadley cell, it's colder down here. So this current, this wind, southwesterly winds, increases in strength. You get shifts in the you get a large increase in the strength of the ACC as it gets colder. The temperature gradient to the equator increases, right? The currents get stronger. The Hadley cell retreats. It doesn't extend down as far, right? It's more like 35 degrees south, right? It's moving this way. And then what happens is the early Pleistocene, it got super cold. So we got a huge growth of the Antarctic ice sheet. We've got a large increase in sea ice growth. The Hadley cell shrunk right back. And it only came down to about, 30 degrees south, right? The temperature gradient is much larger. And so we get a large increase in the winds around Antarctica. We get everything moves outward to higher latitudes. The polar front, the other fronts, the northern boundary moves out much further from Antarctica, and the ACC gets much stronger. It's a much colder world, okay? So that's sort of the shifts that occur. So what we're doing with global warming and climate change is we're heading over from here, states like this, to states like this, to states like this. You know, we're getting huge global changes as a result of what's going on, and the ACC is changing significantly. Okay, so that's one of the one of the things that's going on. Okay, so basically, there's lots of other details. There's an appendix full of stuff, lots of other details of what's going on, but the gist of this article is that, we're making, with our warming of the planet being so fast, we're heading into a lot of unknown territory, right? We're changing things so much more quickly than any changes have occurred in the paleo records, right? And we're moving into really unknown territories. So yeah, it's very, very significant paper, significant work, right? We're changing the climate system so much that we're changing the actual massive heat transfer mechanisms on the planet, in the atmospheres with the jet stream changes, and in the oceans with the ocean changes. So the changes in the largest ocean current on the planet, the Antarctic Circumpolar Current, right? It's the world's most powerful and consequential mover of water, right? Carries more than 100 times as much water as all the world's rivers combined, between 162 and 182 Sverdrups of water. And in recent decades, it's been speeding up. And this, of course, is likely to change the amount of carbon that's absorbed in the southern oceans, right? It's basically 40% of the carbon in the atmosphere ocean system is, goes into the sink of the southern ocean. So that's going to be changing. And, loads of other things as well. And, this is a current that's been around for a long time. Right after Antarctic drifted away by continental drift from South America, it opened up that channel in the ocean, a gateway. The ACC, Antarctic Circumpolar Current, developed, you know, it was millions of years after the 34 million year ago separation, but it was pretty much flowing as it is today in its modern form 12 to 14 million years ago. Sorry, it's 165 Sverdrup to 182 Sverdrup. The strength of the winds over the Southern Ocean have increased about 40% in the past 40 years. Right? So among other things, it speeded the ACC, it's energized large-scale eddies within it that move more and more warm water from higher latitudes towards the Antarctic ice. And yeah, so basically, you know, we're monkeying around with very large-scale systems on the planet. The ocean waters ringing Antarctica currently absorb about 40% of the carbon that humans introduce into the atmosphere. So it's unclear, you know, how the speed up of the ACC will change this, but we're sure it will, probably will. And yeah, so the flows compared to the mean flow of the ACC over the last 12,000 years, the period since the last ice age encompassing the development of human civilization, flows drop by as much as half during cold times and at times nearly double during warm ones. So, you know, we're seeing all of this stuff playing out, and yeah, there's a lot of surprises in the climate system. As Wally Broker said, you know, we're poking the climate system with a stick, and you know, it could act and become a wild beast and, you know, hit us back in the head, basically. Okay, so anyway, it's a very important and very significant new paper. Thanks for listening. Please consider going to my website, paulbeckwith.net, and donating to my PayPal to support my research and videos. Thanks again. Bye for now.